morning, Algebra 2. Here we go, 5-4, factor and solve polynomial equations. This is going to be some review of how we can factor various ways. The ultimate goal would be, we've been working with polynomials and we've been trying to graph them, and we have so far just used either the synthetic substitution to create coordinates, or we could have plugged in x values and found y values like a normal t-table to graph these things. We did know what the end behavior was based on the degree of the function and the leading coefficient. So this is going to help us with another way of being able to ultimately graph these polynomials, and specifically we're going to be using factoring as a method to help us find the zeros of a function. So this is going to be some review of a couple different types of factoring, thinking about GCF, using factor by grouping. We're going to have some special factoring patterns like sums or difference in cubes or a difference in two squares. So let's get going with this, see how it goes. So factoring completely means you have written an expanded polynomial expression into its factored form, and each of those factored pieces are down as far as they can go in terms of I can't pull any other GCFs out. I'm down to a product of unfactorable polynomials. An unfactorable polynomial also is a prime polynomial with just integer coefficients. So that's where we're all the way down factored form. So in A, we have an expanded form, x cubed minus 4x squared minus 12x. We're going to put it into factored form, which means we're creating those pieces that multiply together to produce what you see here. And the very first thing we're going to always consider when we're factoring completely is we're going to look for our GCF, which is our greatest common factor. Now that factor may be a numerical value, maybe it's a variable, it could be both. But we want to look for those things that are in common for each term. Now, with regards to the number part of a factor, you're looking at the coefficients in front of the variables or the constant, and you're seeing if any of those coefficients and constants have the same factor that you could then pull out. In terms of a variable, in this case we have an x cubed, an x squared, and an x to the first. They have at least an x to the first in common, and the quick way to tell what your GCF is for variables is, are the bases the same? And if so, find the base with the smallest power in common. In this case, x to the first is the smallest power in common. So our GCF on this problem is an x. Now what do we do with the GCFs? The GCFs are those pieces that pop out in front of what's going to be left over inside of our grouping symbol. So an x is going to come out from each of those. And then now what we determine is left over is to simply take our original polynomial expression, divide by this GCF. So x cubed minus, or x cubed divided by an x, we have an x squared left over. A minus 4x squared divided by an x is a negative 4x. And a negative 12x divided by an x is a negative 12. Now, you may or you may not be factored completely at this point. You do need to look at the trinomial or whatever's left over in the binomial or whatever the polynomial is in the parentheses and see if you can do anything else. Now, in this case, it looks like we are able to factor x squared minus 4x minus 12 into x minus 6x plus 2. And again, some review if you're doing the box method of factoring here or trial and error, review of the box. The lead coefficient and the variable of the first term, so 1x, goes up top. The middle variable is a negative 4, and then negative 12 times 1, negative 12. And then what's left over in the wings of this box would be the factors of negative 12 that add to a negative 4, so negative 6 plus 2. And that's how we got this. All right, as always, as I'm moving myself through the problems, if you just want to try some on your own, just pause the video. So here we go. We're going to go with these next two, factoring B and C. Once again, looking for for GCFs, and in this problem here, I recognize that each of those 3 30s and 25s, a 3 can go into them, and then x again is my variable common factor. So we have a 3x that pops out in front, and have some trinomial left over inside. 3x cubed divided by 3x is an x squared. 30x squared divided by 3x is a 10x. And 75x divided by 3x is a 25. Now we have another trinomial, x squared plus 10x plus 25. This is a perfect square trinomial. It will factor. And how do we know it's a perfect square trinomial? Well, look at the x squared, that's a perfect square. 25, that's a perfect square. And if I took the roots of each of those, an x and a 5, and I multiplied them together, and then did that by 2, I would get the middle. So we're doing twice the product of these roots here. So this is a perfect square trinomial, which means this will then take the form of 3x, x plus 5 quantity squared. Or x plus 5 times x plus 5. We'll go ahead and just leave it as x plus 5 squared. For C, I have a 5 that's common, and a g to the third that's common. I have a g squared minus a 16. Now, again, we're going back to our properties of exponents. When I have a g to the fifth, and I factor out a g cubed, g to the fifth means g to the cube times g squared. Remember, you add the powers together. So that's how I know what's left over in here after I pull a g cubed out of a g to the fifth. All right, then this thing we recognize, or maybe we don't recognize, but I hope that we get to the point where we do, that that is a difference of 2 squares. All right, and then a difference of 2 squares, that is factorable. So 5g cubed, still out front. Now we get 2 binomials multiplying together. Now what do we do with this difference of 2 squares? Whatever the leading term is in this binomial, we take the square root of the g squared here, and I get those roots in the first position of the binomials. Then we can take 16, and it is also a perfect square, and its roots go at the end of each of those binomials. And then if it's a negative, that means one of these has to be plus, one of those has to be minus. So there we go. So looking out for all these special patterns, all these unique leftovers after we pull GCFs out. Now let's go take a look at some of these special factoring patterns. Now in section 3, we talked about the binomial cubed. Now we have some more cubed things going on, but this time it is a sum or a difference of 2 cubes. So we have a cubed, b cubed, sum. We have a cubed, b cubed, difference. And these two factor into these unique binomial, trinomial combinations. I just recommend that you know this. Just got to commit this one to memory. It's not that hard to do. We'll talk about how we can remember which pieces go where and what sign values are. Let's talk about the pieces first. So how do we know what fits inside the binomial and what fits inside the trinomial? Well, the trinomial, we'll take a look at that one in just a second. Let's look at the binomial first. If you had an a cubed, some number, some variable b cubed, and a b cubed, and you took the cube root of those, the result would be what this a and b value are. So these are the cube roots of a cubed and the cube root of b cubed are what we use for the values in our binomial. Then, if you took, now we can just focus on the a and the b parts to help us come up with the rest of the trinomial. If I took the a and I squared it, I get a squared. And if I took the b and I squared it, I I would get b squared. And then unique, once more, is the fact that I have this product of a and b in the middle, and that's what we do. We just take a times b. Don't worry about the sign. Just take the values of a and b and multiply them together, and that's what we get in the middle of our trinomial there. All right, now let's talk about the sign. There's an acronym we can use to help us remember when is it positive, when is it negative, and the acronym is SOAP. And that means the same sign, the opposite sign, and then always positive. S-O-A-P. So, what does this mean? We'll use the sum of two cubes to show this. So, in the sum of two cubes, we're adding two cubes. If that's a plus, that means the very first sign in the binomial will also be a positive. Same sign. The second sign, which is now in the trinomial, will be opposite, which is now negative. And the third sign, no matter what it is, sum or a difference of cubes will always be positive. So there's how I can remember how I go plus, minus, plus, or negative, plus, plus, depending on where I started. So let's use this now and apply it to some of these problems. So first of all, how am I going to know I have a sum or difference of cubes? Well, the big giveaway is I'll have a binomial. Second giveaway is I look at each of the pieces. 27, that's a perfect cube. X cubed is a perfect cube. Anytime you have a power that has a variable that has a power that's divisible by 3, that exponent will be a perfect cube situation. And then 125 is also a perfect cube. So you're going to have to know your perfect cubes like 1 through 7 to recognize maybe the coefficient and the constants. But again, variables, look for the power. If the power is divisible by 3, then that power is a perfect cube. All right, now that I do that, so right now this 27x cubed plus 125 is in the form of an x cubed or a cubed plus b cubed. We're going to make it look like now a plus b and then a minus ab plus b squared. So we just need to identify all the a and the b parts to be able to write this thing. All right, where does the a part come from? It takes our 27 x cubed, and we're taking the cube root of 27 and the cube root of x cubed, and then what results is the 3x. So this is our a value. We do the same thing with 125. You take the cube root of 125, and what results is 5, and that's our b value. All right, so far we're going to get an a, which is our 3x, and our b, which is a 5, and we write that as our binomial. Now to fill in the rest of the trinomial, we can use the 3x and the 5 to come up with that. Oops, forgot to square my a there. All right, so the next term in the trinomial, the a squared term. So whatever a was, in this case 3x, if I square it, I get 9x squared. That's what's going to go right here. And then 5, if I squared it, I get 25. That's what goes on the end. I follow my sign SOAP. What's in the middle is the product of a and b. So multiply 3x and 5, and we get 15x. And then I follow my same sign, opposite sign, always positive. And there is your factored form of 27x cubed plus 125. Let's try b. So I'm going to factor out of here. I notice that I have a 2 and a 250. A negative 2 and a positive 250. And I have a d squared and a d fifth. D squared is the smallest common power that can come out. 2 can be a positive 2 or a negative 2. I am going to pull out that negative, and I'd say probably get in the habit of pulling the negatives out. So there's my GCF that comes out. What's left with this is a d cubed minus a 125. So when you first looked at the problem, you might have said, oh, well, we've been working with sum or difference of cubes. That's what this must be. But you cannot forget the very first thing we talked about in this lesson, which was pulling out GCFs. So I don't have a sum or difference of cubes until I pulled out that negative 2d squared. And now, here, I have a difference of 2 cubes. All right, so that negative 2d squared stays as part of my problem. And then I go ahead and I think about my d cubed minus 125. D cubed, well, the cube root of a d cubed is a d. The cube root of 125 we just worked with was 5. And if my sign to begin with is a negative, that means this will be negative. If I square d, I get d squared. My first part of my trinomial. We do the opposite sign now. Multiply d and 5, so I get 5d, always positive. 5 squared is 25. That is my solution for d there. Now when you're doing the sum and difference of cubes and you get down to the trinomial, I know it might look like it's factorable. This part might look factorable, but it won't be. And so when we start talking about zeros and things, or solutions or roots, that d squared plus 5d plus 25 would give me imaginary. It wouldn't give me real solutions if I were to factor it, set it equal to 0. So can't typically I won't be able to factor that, give real solutions. I'll get imaginaries from that. But that's coming up later. All right. What about another way of tackling problems? What if there are more than 3 terms? Well, this is called four-term polynomial. This factor by grouping is an approach that can be used to take care of terms that are paired together. When we have 4 terms, we can maybe group some things together. So here in this example, we have our first 2 terms have r in them, RA and RB. And our last 2 terms have s's in them, and they also have an a and a b. And so if you group them, where you looked at pulling out of the RA plus RB an R, and then pull out from the SA and SB and the S, then you have a situation where you ended up with a binomial of A plus B with each of those pairs. And that's what you're looking for. You're looking for a common factor of these pairs that you have pulled the GCF out of. And that common factor becomes the GCF for the entire group, and now we can write it as just A plus B, and then R plus S is left over, and that's what we get for our second binomial here. So these will become binomial times binomial look to them. I don't have to pair the first 2. I can maybe work with the first and the third, or the first and the fourth. So just, you're going to have to go and play around with it. Okay, in this example, we're going to take a look at pairing them 1, 2, and 3, 4 for the purpose of looking at what's called an opposite. So I'm going to put parentheses around them just to indicate how I'm pairing them. So don't think I'm saying let's change this to a multiplication problem. So I'm going to put a parenthesis around that group, and then I'm going to put parenthesis around the negative 3t minus 5 group. Again, I'm not making this become multiplication. I'm just showing you how I'm going to pair it. All right, so in the first blue group, I noticed that 27 and 45 are both divisible by 9. And a t squared, t to the third, the smallest power they have in common, is a 9t squared. So that's what comes out first from the blue group. I'm going to have a 3t plus 5 left over. In the red group, I noticed that out of the 3 and the 5, there's nothing in common, and the t is by itself. So what do you do here? Well, if you look at the blue 3t plus 5 binomial that we just found, and you consider the red group of negative 3t minus 5, you'll notice that each of those are just opposites of one another. Positive 3t, negative 3t. Positive 5, negative 5. These are opposites. And when you have opposites, you can pull out a negative 1. what happens to the red group. To make it look blue, I pull out a -1. I get a positive 3t plus a 5. And now those two things are the same. So we started with opposites. This is what you're going to want to look for in these things. When you're doing factoring by grouping sometimes, you won't be able to pull something out of that red group other than a negative. And that changes myself to a negative times a quantity of a 3t plus 5, and now I have two 3t plus 5 binomials, which is what I'm after. So that's what happens here. I pulled out that -1. I was left with the 3t plus a 5, and then I see 3t plus a 5, 3t plus a 5. There's my common factor of this big group. And then I notice I have a 9t squared minus 1 left over. So we're going to write it. 9t squared minus 1. That pairs together. 3t plus 5. Because that's my GCF of those two binomial, single, monomial products right there. And then, not all the time, but in this case, this is a difference of two squares. Difference of two squares. And that means we're able to factor that. And that becomes negative, or 3t plus 1, and a 3t minus 1, and a 3t plus 5. And now finally we get down to our factored form of that first factor by grouping problem. Let's try with B. I'm going to again consider pairing the groups here as they are. So in the green group, looks like I can pull out an x squared and have an x minus the 3 left over. In the red group, looks like I can pull out a 6 and have an x minus the 3 left over. That's good. I ended up with 2x minus 3's. So I have an x squared plus a 6 group and an x minus a 3 group. Can't do anything with x squared minus 6, so I am done at that point. Okay, again, you don't always have to pair the first two. Like, what if I were to consider pairing these two together? Pull out an x, and I get an x squared plus a 6. And then, what if I considered then the leftovers? Let's pull out a -3, and I have an x plus a 6. Well, look at that. Or an x squared plus a 6, sorry. I noticed that I have two x squared plus 6's, and there's my x minus 3. So I would end up with the same thing. So sometimes you could pair them differently. All right, factor by grouping. Then we move on to our other form. This is a way of tackling some things that look to be like a standard form quadratic, but are not. Maybe because their powers don't go to one constant. And this is called quadratic in form. And we're going to use, I'm going to discuss this with the use of substitution. So these u's that you see in the problem, they are going to be substituted values. And what I mean by that, you'll see in just a second. So quadratic in form means I want my expression to look like our standard form quadratic. Ax squared plus bx plus c. All right, this very first one doesn't really necessarily fit into the quadratic in form, but let me show you how we can tackle this one. 10 is really the only thing I can factor out of this. And I get that. Then, noticing x to the 4th minus a 1. That x to the 4th is an even power, so it's perfect square. 1 is a perfect square. So this is a difference in two square problems. X squared plus 1, x squared minus 1. And then I notice x squared minus 1. There's another difference of two squares. So we get x squared plus 1, and then x minus 1, x plus 1. How it could have been quadratic in form is you could have substituted something in for x to the 4th. And we're gonna talk about that in this next problem, because this next problem lends itself a little better to seeing substitution. All we have trinomial, and I see, look for my GCF first of all. Again, I always look for the GCF. I have 3m squared as my GCF. So 3m squared, and I'll be left with an m to the 10th power plus 3 into 54 goes 18 times, m to the 5th, remember you're adding your exponents using our properties, and then 3 into 51 goes 17 times. Alright, now here, it's m squared plus 18m to the 5th plus 17. This is where we will look at using substitution values. 3m squared is going to be a part of my solution, so we don't want to forget to put that in at the end. Now, what I notice for quadratic in form, and this is what I look for, I have a trinomial, and I notice that my power of my middle term is always half of the power of my leading term. When you have that, when the power of the middle is half the power of the lead, or just look at it as the lead power is twice the middle, same thing, then you have quadratic in form. Now, I'm going to show you this using the substitution method. If you're going to do the substitution method, whatever your leading, your middle base power number is, in this case, m to the 5th, that's what we use as our substitute value. Now we're going to use the variable u as my substitute value here. So I'm going to use u. And we're going to change this m 10th, 15, or 18m to the 5th plus 17 to now become variables of u. So here's something to think about. M to the 10th, that is created from an m to the 5th being raised to a second power. And if m to the 5th, though, is equal to u, then that's where u squared is going to come from. And I'm going to rewrite this problem now as 3m squared times, actually I could probably just ignore the m squared. We're just going to work on the m to the 10th plus 18 m to the 5th plus 17. We're going to work on this part, and we're going to do our substitution here. So we just said that m to the 10th was equal to u squared. So that becomes u squared. M to the 5th by substitution value is just u. Bring in this. So now that u squared plus 18u plus 17 looks to be quadratic in form. A x squared, bxc type of a look to it now. And then I can factor this. I get a u and a u and a 17 and a 1. Factors like that. Now, I'm not done though, because our original problem had the variable m. So now we got to come back and think about substituting m to the 5th in for our u values. So we put that m to the 5th back in, and we get m to the 5th plus 17, and m to the 5th plus 1. And now finally we can go ahead and finalize our answer, including that GCF that just came out. Can't forget our 3m squared. So we have 3m squared that came out front, and then we factored and got m to the 5th plus 17, m to the 5th plus 1. And now you are factored. So that's using a substitution method. And again, identifying that the middle power is half of the lead power. Whatever that middle power and variable combination is, becomes your substitute value for u. Plug it in and solve from there. Don't forget to once you get to the u plus or minus times u plus or minus binomial, so once you get to this part, sometimes we get here and we just stop. We have to remember to reapply our substitution values so we can get our final answer. So that is quadratic in form. Alright, let's try some solutions here now. Where before we were just working with expressions, now we're going to find some real number solutions. So notice now these are equations, which means we will be factoring, but we'll be factoring setting ourselves up equal to a 0. And when we set ourselves our polynomials equal to a 0, that means we're looking for the zeros, another name for x-intercepts. And this, again, is what we're going to use to help us graph these things. All right, so looking at A, we will put ourselves in descending degree order. I like to leave my lead coefficients positive. So that means this 12x cubed would subtract to this side, and my negative 16x would add over here, and I get 2x to the fifth times 12x cubed plus 16x is now equal to 0. So we're going to use this factoring practice we've been working with, and then come up with actual solutions. So, on the left-hand side, looks the only thing I can pull out is an x. That's my GCF. I'm left with a 2x to the fourth minus a 12x squared plus 16 equals 0. Then I have to decide what am I going to do. Well, I have a trinomial here where the power in the middle is half of the power of the front. And so here's a situation where I might say, let's let u equal x squared. And if that's the case, then x to the fourth, once again, is found by x squared squared, which is where u squared is coming from. So if you always let the middle power become u, then that means the front power that's twice the middle one will always become your u squared component of this quadratic form. All right, so we're going to factor the trinomial here using our u's. We would get 2u squared minus 12u plus 16. So I'm just taking this and we're putting it in with u's instead of x's, and we're going to factor this. I should have pulled out a 2 the very first time. Wasn't paying attention. So let's pull out a 2 instead up here at the top. Pull out that 2. Let's change this. We're going to rewind here. Sorry for that. All right, GCF of 2x left with x to the fourth minus 6x squared plus 8. All right, once again, u is equal to an x squared, so we have, again, just working with the trinomial, we get a u squared minus a 6u plus an 8. This will then factor u minus 4, u minus 2. And then I have to reapply my substitute value, so put that x squared back in. And I have a situation where, there we go, that x squared minus 4 is factorable because it's a difference of 2 squares. So we're going to put, first of all, we're going to stick our GCF back into the problem. So we're going to come back in here, stick our GCF in. I'm going to factor the difference of 2 squares. That's going to become x plus 2, x minus 2. And then we have our x squared minus 2 at the end. Remember that all of this is now equal to 0. And then now we use our zero product property. So here, let's go up here. Zero product property. CPB. Zero product property says that any of those factors, if they were a 0, would make the solution to this product equal to 0. That means we take every factor that has a variable in it and we set it equal to 0. And this is how we find all of the possible values of x that make this thing true. Well, this one, divide by 2 and you get x equals 0. This one you subtract 2 and x equals negative 2. This one you add 2, you get x equals positive 2. This one, we have x squared is equal to 2, and then we have to take a square root. So x equal to plus or minus the square root. So we have 1, 2, 3, 4, 5. 5 x-intercepts that would help me come up with parts that I can use to this polynomial. Now, interestingly enough, 5x-intercept, and we had 5 as our highest degree. And that will always be the case. You would have the degree, highest degree, tells you the number of possible real solutions. You don't have to have 5 real. You might have 3 real and 2 imaginary, but possible 5x-intercepts, and that's what happened. That's how it played out in this problem here. So those are our solutions then for all the values of x that would make this thing true. So we're using quadratic form in that example. What about this one? Well, let's see what happens here. Once again, I'm going to look and put all of my terms on one side. I'm going to add that 6x, negative 6x to the fourth, and put it on the left-hand side here. Minus 27x cubed plus 15x squared now equals 0. Don't forget the equals 0, because then you'll forget you're solving. 27, 6, and 15. 3 x squares as my GCF. So 2x squared minus 9x plus a 5 is equal to a 0. And let's see, that trinomial there will be able to factor. See what happens here. We want a negative 5, so there's negative 10 plus 1. Now that'll give me the negative 9 in the middle, but notice it doesn't give me the positive 5 here. So we need to try and rearrange our values here to make this thing work. Or it's not factorable. 2x squared minus 9x plus 5 is not factorable. We have to go about finding our zeros another way. So how would we do this? If we weren't able to factor, we would use quadratic formula. So, oh, I forgot to show what happened here. If we just rearranged. So let's rearrange. All right, what if we put the, let's say we put the 1. Now we got a 2, we got a 5. Yeah, that's not going to give me that 9. And so I really am kind of stuck in terms of factor. So let's see. This is going to possibly give me some imaginary solution, but let's go ahead and put 2x squared minus 9x plus 5 into our quadratic formula. And we get x is equal to negative b, so negative of negative 9, plus or minus the square root of 9 squared minus 4 times 2 times 5, so that's minus 40, all over 2a. So 2 times 2. We get 9 plus or minus the square root of 39, all over 4. And those are real solutions. The square root of 39 is just, in terms of it, we won't make it a decimal number. We'll leave it as a simplified radical. It's just the square root of 39. So in this case, we get x is equal to a 9 plus the square root of 39 over a 4. Or a 9 minus the square root of 39 over 4. Both of them being real numbers. You could go ahead and just leave that as your answer. You don't have to separate it. All right, so those are 2 of my x's, but we can't forget this guy. Remember we factored out that 3x squared? So we have to consider for zero product property what we would get there. Divided by 3, take square root. You get x equal a 0 there. So what are my real solutions? They are x equals 0, and they are 9 plus or minus the square root of 39 over 4. There we go. So finding our real solutions through the use of, in the first example, quadratic form. The second example, we did GCF, and then we were unable to factor, so we used quadratic formula. All right. Our application to this thing. So we're designing fish tank that is to have a volume of 40 units cubed. Find the dimensions of our tank. Okay, so this is a rectangular prism, and the volume of a prism, rectangular prism, is equal to the length times the width times the height. So maybe when we're talking about volume, generically, we start there. Length times width times height. Now this is all supposed to be equal to 40 units cubed. So let's put in what we know for length, width, height, and for volume. So volume we know is 40. Now, it would be great if that was 0 equal to 2x times quantity x minus 1 times x minus 4, because then I could use zero product property to find x. It's not. And I can't just simply subtract the 40 over and then work that out with zero product property. I first have to go ahead and figure out on the right-hand side what will be the expanded form of 2x times quantity x minus 1 times x minus 4. So we're going to go ahead and do that. We're going to FOIL the two binomials and get an x squared minus a 5x plus a 4. Then we're going to distribute that 2x and get 2x cubed minus 10x squared plus 8x. Now I'm ready to bring the 40 into this problem. We're going to subtract the 40 to the right-hand side, bring it over here, and I get a 0 is equal to 2x cubed minus 10x squared plus 8x minus 40. Then I look at, I got 4 terms. Maybe we can group them. Let's see what happens if we group them. I'm going to group those two together and pull out a 2x squared. Be left with an x minus a 5. And then I'm going to group these two together and pull out an 8 and be left with an x minus a 5. Well, look at that. Pull out a positive 8. That's good. There's my two binomials that are the same. So by grouping, I know that I have 0 is equal to 2x squared plus 8 times x minus 5. All right, we're ready at this point then. We have two factors. They're equal to 0, so we're ready to set up our zero product property. We can say that 2x squared plus 8 is equal to 0. And we could say that x minus 5 is equal to 0. Well, 2x squared is equal to negative 8, and x squared is equal to negative 4, and x equals, plus or minus 2i. That's not a real solution, so I obviously won't have that as part of my answer. And here, x equals 5. So there we are. We don't know what the units are, so we have x equal 5 units. Let's go ahead and put a u there. That's what I would have to be in order for this fish tank to have a volume of 40 cubic inches, given those dimensions.